Okay, good afternoon, everybody. So what I'll be reporting actually is the crystal growth in chapter 3, wherein this is mostly on the normal and the layer growth on the rough and flat crystal surfaces. We've discussed briefly on actually the theory and the background for this in the previous slides by Dr. Cyril. But just first imagine, like, have you ever wondered how come crystals grow in such a manner? So for example, in this case, for the left side, we have a water droplet at super cold temperatures producing a hexagonal shaped snowflake. Whereas here on the right, you can see a cubic salt crystal in a super saturated solution and eventually growing into a really nice crystal, uh, a really nice crystal. Yeah. So just looking at these properties, there are ways or different characteristics in order to grow these kinds of crystals. And just going over with the concept first, let's try to visualize the crystal growth models. So what I'll be Okay, so again, taking off from where we are, again, we need to visualize first the crystal surface. In ideal crystal, we could just imagine a defect-free crystal face. So in this, it's a very smooth surface. But do recall in the previous in our lectures that for infinitely flat surfaces, there's really a high amount of pressure that's really needed in order to be defect-free. And in the real world, realistically, it would develop these kinds of rough crystal faces as discussed in our previous slides and lectures. And what I'll introduce as a concept is actually a TLK model, which are terraces, ledges, and kinks. So in our textbook, the ledge is more or less the step. The terrace is still the monoatomic layer on top of these lower steps. Likewise, the kink are these uh, layers or locations in between these kinds of steps or ledges. Now, to think of these TLK model, just to illustrate also, if we have these kinds of crystals in a super saturated solution, the tendency, actually the very important factor for crystal growth are the kinks. So more kinks would lead to faster crystal growth. So if you can imagine, similarly, if we have a lot of these atoms inside a solution and trying to grow the crystal, if these atoms do adsorb onto our terrace site, basically there are just two saturated bonds that's bonded into this terrace site. And if you go towards the ledge or to the step, you can see the bonding there coming from the step and likewise on the bottom terrace. And similarly on our kinks, so these have three saturated bonds and likewise three unsaturated bonds. Therefore, it's really important that these kink sites are studied and determined for our crystal growth. So this is the fastest crystal growth across all these three layers or three areas of attachment. And likewise, if you can just think about it, given that the three bonds there, it would likely stick compared to those in the terraces or in the flat surface, leading to additional crystal growth of these atoms. Now, if you try to look into the energy diagram of these kink sites, there are some references on trying to look at the most favorable or thermodynamically favorable sites within these crystal growth. So there are some adsorption into the lower terrace layers. But if you can see that the lowest energy that we have in the solution is this point here between the terrace and step. Ideally, because of the better bonding, it requires lesser energy actually as well, compared to that in the absorption layer or even on the top terrace layer. Okay. So likewise, what we'll also discuss is, or at least in this chapter, is this is also kinetically feasible. So we are thermodynamically favorable on the kink sites and likewise kinetically feasible. And its rate of growth is expressed as by this expression here. So what we have is, this is the rate of growth R. We have the A as the interatomic spacing or the lattice spacing constant there. This delta here would be the average kink site spacing. And this whole term here that's squared would be the probability to find the kink site. These terms J plus and J minus are more or less the attachment flux and the detachment flux respectively, which are proportional to the rate constants of the energies of this system. To discuss this more further, at least to explain this rate of growth, we could expand that equation actually if into this equation here as presented also in our chapter book. But just to break that down into simplifying the same equation as before, this is still the probability to find the kink site. This whole term here that I bracketed would be the attachment flux. And likewise, the negative symbol here on the right would be the detachment flux. Now, if I highlight that top rightmost layer term, that delta U or the chemical potential, if we try to consider this delta mu to be really, really small or equal to that of the Boltzmann constant times temperature or a very small supersaturation, what we note is that this term approaches to 1, and likewise, this results to our rate R to decrease proportionally. Hence, the first item to understand in terms of the rate of growth for normal layers in our rough surfaces is basically if there are low supersaturation solutions, likewise, the rate of growth is also less. So we do also recall that for this case and our chemical potential, in our chapter 1, this is similarly to that of the concentration over our equilibrium concentrations, or likewise the current pressure of the system over the equilibrium pressure of the system. And likewise, as you go towards from the right side, so again, it's coming from a vapor phase to a crystal phase. And if you go towards on the left side, so decreasing chemical delta potential, it would more or less be a crystal phase favorable to a vapor phase, so leading to less growth, or actually just solubilizing our crystals. Okay. Now, if we look into the highly supersaturated solutions, I mentioned that if it's low supersaturation, it's low rate of growth. So similarly, if we look at melts, so these are just some simplified just condensed equations for melts. This beta sub m would be our kinetic coefficient for crystallization in melts. Again, similarly, we just took these expressions out and factored a constant here called beta m. We also have these kinds of similar equations and formula wherein we have this beta s. This is the kinetic coefficient in solutions. And you can see how these beta and the rate of R and the C behaves against this graph here that I'll show on the right. So on the bottom x-axis shows the difference in our concentration with that of the equilibrium and the rate of growth here on the y-axis. And I mentioned that supersaturation is a big term for rate of growth. And if you can see on the far right, upper right there, the term becomes very linear because that whole term basically just equates to a linear term. For example, R equals beta sub m times delta t. And this would be really linear. On the other hand, if you look at the non-supersaturated solutions, there is a nonlinear growth. And I think this would be explained later on as there needs to be a 2D nucleation first in order to create these kink sites prior to the growth of our crystals. So you can see this relationship here, more or less how our crystals grow coming from a low concentration up to a very high concentration. So similarly, we have these important factors. We have C, we have also this probability to find the kink site. So for our concepts, in the normal growth regimes, more or less these two factors are the ones that dominating the rate of growth. It's the concentration to be highly supersaturated, and likewise the presence of the kink formation. So again, many kink sites would lead towards to higher beta and likewise higher rate of growth. There are also other equations. So you can see these are in the different phases. We have rate of growth in melts. We have rate of growth in the solution. And likewise in the vapor phase going to a crystal phase. And you can see these terms here that I've encircled, the T, concentration and pressure, they are also proportional to how much of the supersaturated solution around your environment or around your system would be deposited onto your substrate or to your crystal. Okay. Now, if we question then is how about those layers that are flat or let's say very ideal crystals or without kinks? I mentioned that in the very low supersaturation solutions, you need to have a 2D nucleation first. That is actually the first step for atomically smooth surfaces in order to grow. So these surfaces are impeded and needs to form these ledges or steps first prior to getting some kinks, and those kinks would be the sites to grow of the crystal. So more or less, there would be a higher energy requirement to nucleate these kinds of defect-free crystals. And you can see and also recall that there are some critical size that's dependent on our pressure or concentration of the system with that of the specific surface energy of that crystal. So also recall these in our Laplace that there is more or less a critical size before these kinds of crystals grow. So if you look at the diagram below, basically an add atom or an atom that adsorbed onto the terrace is not favored. But if you apply enough energy, this energy there would allow this kind of a step or ledge formation. And eventually the ledge would grow. And eventually again, these would have kink sites for other atoms in the solution to grow. So energetically speaking, the first step here going from the terrace or a flat surface to a ledge formation is the one that's limiting. And basically, this would be a rate determining step. And this is something that will be discussed further on in the next sections. I think Zab will cover this for our rate of advance of the steps. But in general, what we have for this case is that these growth rates for a flat surface is dominated by this equation here, R equals PV, which is again the rate of growth equals the density of these ledges times the velocity of these ledge or the step advances. And more or less, these step advance is basically just a geometric calculation on how much of these layers, these monoatomic layers, grow on a specific angle and a specific height on a specific length lambda. Okay. So again, these velocities would be really covered on the next few steps, actually on the rate of the advance of the steps. But at least for us in this case, in this slides, we do know that before growing these crystals, a ledge must be formed. Okay, so there are some examples of these ledge and step growth at supersaturated systems that I also collected on other studies. So for example, here on the left side would be the dependency of the step advance versus that of the concentration. Similarly, if you look at the broken dashed line there, so if we say that the crystal is initially rough already, then the concentration, or rather the step speed or the rate of growth is proportional to that of concentration. But for systems with very low kink density or atomically smooth surfaces, basically there is this this lag time before growing the crystals because it needs to create these kinds of steps first. And similarly, there are some dependencies of these step growths, likewise with the material step energy. So what you have here as an example are difference between low surface energies and likewise high surface energies. And these, in cases, in these studies, there would be also differences in our step counts depending on the surface energies of these systems. So more or less in summary, the roughness of the crystal will generally affect our crystal growth. We do note that kinks more or less are the sites that are favorable in order to grow. And if we have more kink sites, if we have more rough sites, it would have a faster rate of growth. Similarly, if we do have a lot of concentration of these atoms or pressure of these vapor atoms, basically there's a lot of attachment flux and a faster crystal growth. For the cases of defect-free or smooth crystals, They can still grow, but their kinetics are hindered. Again, it's a new ledge is the one that's the rate limiting step. So it must be formed in order to grow these kinds of kinks. And similarly to the first video that I presented in the first slide, there is also a dependency on our material. So the surface energies of material, the pressure of the system, likewise the other lattices, for example, the snowflake on the water being hexagonal or tetragonal rather, and salt crystal as cubic would also have different growth shapes. Okay, and that's about it. I have my references and citations here, and thank you again for listening for this coverage.
This will be the outline of my discussion. So I will just give you a brief background of the topic, then the different growth mode by 2D nucleation, and then the main topic about multilayer growth mechanism, and some key points as a summary, and then the references. So sa background, nucleation is the initial process that occurs in the formation of a crystal from a solution, a liquid or a vapor, in which a small number of ions, atoms, or molecules become arranged in a pattern characteristic of a crystalline solid, forming a site upon which additional particles are deposited as the crystal grows. Molecularly smooth crystal faces, free of screw dislocation emergence points, are known to grow by formation and lateral spreading of two-dimensional nuclei on them. So Gibbs was the first to suggest this mechanism of crystal growth. According to Gibbs, the continuous growth of a given crystal face is impossible unless new layers can be formed. The formation of a new layer is difficult at the beginning or immediately after the start of the new layer formation. So I'm just captured here a diagram illustrating nucleation and crystal growth, and this is the reference. So let's now go to the growth by 2D nucleation. So we have basically three modes of growth through 2D nucleation. The first one is the mononuclear layer by layer growth. This is the growth when next atomic plane nucleates after the completion of the previous one. This mechanism dominates if nuclei is small. The second mode of growth is the polynuclear layer by layer growth. This is the case which may become predominant as the nuclei becomes bigger. And then the last mode of growth is the multilayer growth, which is our main topic for today. So what is the multilayer growth? So as mentioned earlier by Bing, I saw her that she captured this already. The multilayer growth is the growth mode in which two or more monolayers, or what we call ML, grow simultaneously. So comparing it to the layer by layer growth, this one is the growth of the ML simultaneously. This is the case when nucleation of the next atomic plane takes place before the completion of the previous one. So I've taken this one from our textbook. This is from figure 3.19, just an illustration of the multilayer growth of a crystal face with a size L by 3D nucleation. So let's discuss the multilayer growth mechanism. So we consider a crystal face with a monolayer island growing onto it with a rate of V. So at a given moment, when the size of the island reaches a lateral size L, a 2D nucleus appears on top of it. The frequency of nucleation on top of the island is given by this equation, J sub 0 or J naught is equal to J naught L squared, where J sub 0 here is constant. And the average time elapsed from the moment of nucleation of the first island to the moment of nucleation of the second island is given by this equation, L all over mu is approximately equal to 1 over J naught. the mu here is the rate of lateral growth and linearly depends on the supersaturation. So we then find the mean size of the lower 2D island when a new 2D nucleus is formed on top using this formula. So L is approximately equal to mu divided by J naught. So the lateral size is equal to the rate of lateral growth divided by the nucleation frequency, and is given by this equation 3.103. Thus, the critical island size for the second layer nucleation is larger, and the larger the rate of island growth is, the smaller is the nucleation frequency. So bearing in mind that this equation from 3.113 will turn out to be L is equal to V over J naught raised to 1/3, we can find the rate of growth of the crystal face proportional to J naught L squared multiplied by A, which is equal to the height of the step originated by the nucleus. So we can get the equation 3.114, which is this one. And this above expression is valid for two cases. The first case is the polynuclear layer by layer growth. This is where when 2D nuclei belong to a single layer. Or the second case is the multi-layer growth, or the polynuclear multi-layer growth, where the formation of mounds or stacks of 2D islands are on top of each other. So another equations here. So we have a previous section which is under section 2.8. The topic is about rate of 2D nucleation. From the equations 2.89, 2.92, and 2.99, we can derive an equation for the rate of 2D nucleation based from the pre-exponential factors given by these three previous equations tackled in section 2. So the rate of 2D nucleation is proportional to the square root of the supersaturation, and the rate of step advance is a linear function of the latter. So we can find that R is equal to this constant multiplied by delta U raised to 5/6 exponent negative delta G over 3kt. So this constant here is equal to this equation, and this constant here is particularly applicable for the case of growth from solutions. Okay, now, so let's study this graph. So this is taken from our textbook in figure 3.18. This represents the supersaturation dependence of the rate of 2D growth in the case of the layer by layer growth, which is this curve 1, and then the multi-layer growth, which is curve 2. As mentioned in the book, the rate of growth does not depend anymore on size of the crystal, but still a critical supersaturation should be overcome in order that the growth to take place. And according to this figure 3.18, the critical supersaturation should be smaller than the one calculated on the base of the layer by layer growth. So just a summary of how the multi-layer growth happens. So initially, perfect crystals grow by the mononuclear layer by layer mechanism up to a critical size determined by this condition, n equals 1 or L is equal to V over J naught raised to 1/3. And beyond this size, gradual transition from the mononuclear layer by layer growth to polynuclear layer by layer growth happens. And then the multi-layer mechanism takes place, in which case the L is now greater than V over J naught raised to 1/3, or N is equal to greater than 1. So in this way, the multi-layer mechanism says that the new nuclei will form on top of the growing ML before the latter is completed. So just taking it in the figure, so the first step is a mononuclear layer by layer growth, then followed by the polynuclear layer by layer growth, and then the last step is the multi-layer growth. So we're going to study again another graph. This one is also from our textbook, figure 3.21. This is the plot of the rate of 2D growth as a function of time in terms of the characteristic time. Curve 1 represents the layer by layer growth. The curve 2 represents the multi-layer growth. And then the curve 3 is a result of a Monte Carlo simulation method. In this graph, how can we obtain the growth rate? So the growth rate is represented by this equation. R sub 1 is equal to A d theta sub 1 over dt. So this theta is the surface coverage of the first monolayer. And then completion with time of the first monolayer follows the time law, which is given by this equation 3.116. The rate of deposition of the first monolayer increases parabolically at short time, given by this graph, and then displays a maximum at Tm, which is given by this equation, and then decreases exponentially at large times up to the completion of the layer. This equation 3.116 describes the behavior with time of the layer by layer growth when each layer is initiated by several nuclei growing simultaneously. As mentioned also in our textbook, the theoretical treatment of the multi-layer growth is complicated and has not been solved analytically up to now. So in order to study numerically the time evolution of the separate monolayers and growth front, a Monte Carlo method is usually used. So for the case of multi-layer growth, if we take a look at curve 2, in the beginning of the process, the growth rate displays several oscillations as shown here, or a series of maxima and minima, and then which gradually attenuates due to the thickening of the growth front. So that's the representation of curve 2. So the formation of the 2D nuclei of each new layer depends on the following. First, the surface coverage of the preceding one, or the probability that there is crystallized part of the underlying layer just under the 2D nuclei. So here are some equations again. So equations 3.107 up to 3.107 double prime. So differentiating the equation 3.107 prime, we often use this expression to calculate the growth rate of the 2D island. So this is the equations we have for the growth rate. So in order to find a solution of equation 3.117, we need to determine the probability rho n minus 1 times t prime, and this is used, we often use the mean field approximation, assuming that the probability is equal to the surface coverage of the preceding monolayer. So there's another graph here. So it's the taken again from our textbook, figure 3.22. So this is the representation or of the variation of with time of the rates of growth of the separate monolayers. So in this case, this is the case of steady state multilayer growth. The curves are shifted by a period of t, represented here. Once the monolayer is completed in a time interval t prime, the overall rate of growth is represented here, and it's also shown by the straight line, which is r is equal to the summation of r sub n. So as shown earlier, I have previously shown the equation 3.117 double prime. So if we integrate that previous equation and it's carried out until the steady state is reached. So the shift of each curve with respect to the preceding one remains constant. And we have another equation here, which is 3.118. And where t here is the period or the time of advance of the front of crystallization by one monolayer. And we also have another equation, which is the steady state rate of growth given by this equation 3.119. And the number of simultaneous growing monolayers is given by T prime over T, approximately equal to 4. So in this figure 3.22, it gives the steady state and shows the sum of the bell-shaped curves. So are shown here in the straight line. So just some key points. The multilayer growth is one mode of crystal growth by polynucleation in which two or more monolayers grow simultaneously. The growth of another layer takes place before the completion of the previous one. And if we take a look at the mechanism, how is the growth is being formed. So the first step is a mononuclear layer by layer growth, followed by the polynuclear, and then the last step is the multilayer growth. As mentioned also earlier, the rate of growth does not depend on the size of the crystal, but the critical supersaturation should be overcome for visible growth to take place. And also, the critical island size for second layer nucleation is larger. And the larger the rate of island growth, the smaller is the nucleation frequency. The last key point here is that the formation of the 2D nuclei of each new layer depends on the surface coverage of the preceding one and the probability that there is crystallized part of the underlying layer just under the 2D nuclei. So my topics is really short, so this multi-layer growth, just one subtopic. So this is the references I use. Main content is based from our textbook and some key references I read for the discussions. So that's my last slide.
Good afternoon. So my presentation would be a continuation of the chapter topic discussed by our previous presenter, Miss Julie. And this is about some particular cases of crystal growth. So the topics that I will be covering are listed in the outline here. So we'll have stages of VLS, mechanism, growth processes of nanowires growth dynamics, the rate limiting process, the growth rate, and the other growth methods of VLS. So to begin, let's have a short review of what is VLS. VLS stands for vapor liquid solid method, and it is a mechanism for the growth of one-dimensional structures such as nanowires, typically from a chemical vapor deposition. So VLS was proposed in 1964 to explain how whiskers grow from a silicon gas phase in the presence of gold droplet upon a silicon substrate. So to further discuss, VLS crystal growth method is typically described in 3 stages. So first, we'll have the preparation of a liquid alloy droplet upon the substrate from which a wire is to be grown. So in the figure here, we have a thin gold film that is deposited onto a silicon wafer substrate, typically by means of sputter deposition or thermal evaporation. And then the wafer is annealed at temperatures higher than the gold silicon eutectic point, thereby creating a gold silicon droplets on the wafer surface. And then we'll have the introduction of the substance to be grown as a vapor, which absorbs on the liquid surface and then diffuses into the droplet. And then lastly, we'll have the supersaturation and nucleation at the liquid-solid interface that leads to the actual crystal growth. So as described in these stages, growth happens by the adsorption of a gas phase onto a surface, but we know that this adsorption process is very slow. That's why there is a metal catalyst, which is the liquid alloy, to make the adsorption very fast up to saturation levels. But how does alloy droplet help in the faster growth of crystal in the case of nanowires? So there are two reasons responsible for the catalytic effect of the alloy droplet. So first, we have the gold silicon droplets on the surface of the substrate, which act to lower the activation energy of normal vapor solid growth. So as shown in this picture, for example, silicon can be deposited by means of this mixture of gases, which has silane and hydrogen. And deposition only happens at temperatures above 800 degrees Celsius in a normal vapor solid growth. But below this temperature, almost no silicon will be deposited onto the growth surface. However, having these gold particles, it can form a gold silicon eutectic droplets that can absorb silicon at temperatures just slightly above 360 degrees Celsius. And then this liquid surface can have a much greater condensation coefficient than the solid surface. That's why it makes the growth of crystal faster. So the image just shows the catalytic effect of the alloy droplet. So if there's catalytic effect, there's also inhibitors, and generally these rate limiting processes are among the most important problems in crystal growth. So in the succeeding slides, I will be discussing about the growth processes that happen during nanowires growth. And then we'll learn among which in these processes is considered the rate limiting or the inhibiting process. But first, let's define the phases and the interfaces in a VLS crystal growth. So in VLS crystal growth, we have 3 phases and 2 interface boundaries. So we have 3 phases, the vapor, liquid, solid. And then we have 2 interface boundaries, the liquid, solid, and the vapor, liquid boundaries. So the growth processes of nanowires are shown in this figure. So we have 4 processes that can happen during the growth of nanowires through VLS. And these are as follows. First, we have the mass transport in gas phase, in which the material is supplied by a gas flow with the flow rate and a gas ratio parameters. And then step 2, there's the chemical reaction in the liquid surface. So the nano droplet is exposed to a gas mixture, usually a silane and hydrogen gas mixture. And then the gold forms an alloy with the silicon and liquefies. And then step 3, we have the diffusion in the liquid to the liquid crystal interface. So this is when the liquid is supersaturated and the silicon precipitates out and crystallizes the nanowires. So this is why we already have here the growth, the starting to growth of the nanowires. And then step 4, we have the formation and growth of 2D nuclei at the liquid-solid interface, wherein further condensation and dissolution of silicon into the liquid and solid interface, and then the length of the nanowires increase. So how the growth is sustained? So in the schematic shown here, it just simply describes the continued nanowire growth in a layer by layer fashion. So first, let's describe the different phases in the material, or the 3-phase boundary. So we have the crystal solid, the supply or the vapor, and then we have the collector or liquid. And then we'll have the nucleation. In this figure, it shows a newly generated nuclei that propagates along the liquid and the solid interface. And then we have the ledge propagation in which the nuclei propagates to form a new ledge or layer or a film. And then the layer is formed until it is completed. And then the process is repeated until the nanowires are formed. So in the image here, it's just an example of a TEM image of a silicon nanowire. So another example in the figure here is the schematic drawing of a structural appearance of the implantation and annealing processes to obtain metal nanoparticles for subsequent growth of semiconductor nanowires. So in this figure, in letter A, we have the room temperature implantation of gold. And then this is how it looks after annealing at certain temperatures. And then after further annealing at relatively higher temperatures for quite some time, we already have this metal catalyst on the surface of the substrate. And then on the image on the right, we have the same images of silicon nanowires grown on gold implanted and annealed silicon substrate. So it is visible in figure A that only in implanted areas where the nanowires grow. So we have an implantation here through masking, and the area on the left here are the area that is unimplanted. And then for figure B and C, just showing silicon nanowires with the gold droplet at the tips. So going back to the described 4 processes that happen during growth of nanowires through VLS, we determine from each which process is the rate limiting. So let's go to each process one by one again. So number 1, the mass transport in the gas phase. So there is an experiment done by Gevorgizov and Chernov to check this, where they have divided the substrate into 2 regions. So one side of the substrate is done to be denser than the other side. And they assumed that the lesser dense substrate will have a greater supply of silicon precursor. However, they have observed that the length of the whiskers or nanowires in the lesser dense part is just equal with the denser part. That's why it was confirmed that the substrate density has no effect in the rate of the growth. And then for the second process, chemical reaction on the liquid droplet surface. So another evidence also is that when using different metals as catalysts, the kinetic coefficient of growth is similar for the different metals. So it was thought that this could have no effect, since increased precursor concentration may not cause higher growth rate, but rather the increase in the saturation itself. And then in the third step is the diffusion in the alloy to the liquid-solid interface. So this can be ruled out as no effect in the rate of growth, since in thicker wires, they grow faster from larger droplets. So it means that larger droplets means that the atoms cover greater distance going towards to the solid liquid interface. And then the fourth process, wherein nucleation and growth on the solid surface under the liquid droplet. So this was considered as the rate determining step, since nanowires that are grown tilted with respect to the solid surface grow faster. So this tells us that nanowires that are grown tilted with respect to the solid surface has faster rate than ones grown vertically, because the whiskers that grow tilted exposes the solid liquid interface more and doesn't require the formation of the 2D nuclei that I have shown in the previous slide. So now we go on how fast the growth is. So first, we discuss about the rate of actual growth. So assuming crystallization on the liquid-solid interface as the rate-limiting step, Yuvargizov and Chernov suggested an approximate expression of the form R is equal to beta times delta sub mu over KT raised to 2. So this is equation 3.154 of our textbook. So the supersaturation delta sub mu here is given in this equation, the equation 3.151. So combining the information about saturation delta sub mu infinity, we'll have this equation here, the equation 3.155. And from the equation, we can see that the supersaturation and temperature affect the rate of the actual growth. And similarly, the specific energy of the crystal vapor interface and the molar volume of the solid liquid is proportional to the growth. Also, larger droplet represents a higher growth rate due to larger collection area. Now, we go on to the relationship of growth rate and supersaturation. So the figure shows experimental data for the growth of a gallium arsenide whiskers at 4 different saturations from the experiments of Yuvargizov in 1975. The y-axis represents the growth velocity, and the x-axis as the wave number. So to further understand the previous graph, let's have a short review of crystal nucleation and growth versus supersaturation. So supersaturation is important because it is the driving force for both crystal nucleation and growth. So nucleation is the birth of a new crystal nuclei, either spontaneously from a solution or in the presence of an existing crystal. While the crystal growth, this is the increase in the size or the characteristic length of the crystal as solute is deposited from a solution. So from this relationship, supersaturation or at lower supersaturation, crystals can go faster than they nucleate. And at higher supersaturation, nucleation dominates the crystal growth. So it means in the figure here, at lower supersaturation, crystal can go faster than they nucleate and would result in a larger crystal size distribution. And at higher supersaturation, crystal nucleation dominates the crystal growth and ultimately resulting in smaller crystals. So going back to the growth rate empirical equation from Yuvargizov and Chernov, one of the discussed disadvantage is that it doesn't account for the intimate mechanism of the 2D nucleation process. So since growth can proceed by the formation of a single 2D nucleus or several 2D nuclei. So the rate of lateral growth of the superficial nuclei is given by Kastchev. So he suggested this analytical approach to the problem, considering that the nucleation rate is consistent with respect to time. So in 2006, he suggested that nucleation is progressive with time, and the equation is given by the equation 3.156 of the textbook. R ISL is equal to V sub ISL times T raised to N. So R sub ISL is the current island radius, while V sub ISL is growth rate constant, T is time, and N is the constant varying from 1/2 and 1. So N is equal to 1/2 in the case of diffusion limited growth, and N is equal to 1 in the case of direct attachment of atom. So since growth represents a process of successive formation and lateral growth of single nuclei, so we have the following mechanism. For mononuclear layer by layer, the growth rate is given by the equation 3.157. And then for polynuclear layer by layer mechanism, growth rate is given by the equation 3.158. So the mononuclear layer by layer mechanism, it is applicable when the whisker diameter is sufficiently small so that the formation of the first nucleus and its fast lateral growth do not allow the formation of another nuclei. And then for polynuclear layer by layer mechanism, it is applicable when the whisker diameter is larger. So there are several nuclei that can be formed on top of the surface of the whisker. So this general equation from Kashchev, we have combined equations 3.157 and 3.158. Then we have the following single expression as the general formula. So this general equation 3.159 from Kashchev shows that the nucleation rate and growth rate constants dependence on radius is neglected as the nanowires become substantially very thin, meaning in the submicron level thin. And it is so, meaning this equation is not valid for very thin nanowires that is already close to the R minimum. So there are two cases here. So for case 1, in this case, the rate of actual growth is independent of the rate V sub ISL of lateral growth of island. And then for the second case, in this case, the actual growth rate of nanowires does not depend anymore on the nanowire thickness. So as my last slide, just to emphasize that the discussions that we had focus mainly on the VLS-CVD method of nanowire crystals. So there are different approaches in growing crystals or the growth of nanowires through VLS. So it can be performed not only by CVD, but also by direct supply of reactant using the following techniques. So we have the MBE, or the molecular beam epitaxy, the MOCVD, or the metal organic vapor phase epitaxy, the CBE, or the chemical beam epitaxy, magnetron sputtering deposition. So there are different approaches, and the selection of each technique, there are several factors on how to select. So primarily, depending on its application, the available technology, and of course, the cost of the technique that will be used. So that would be all for my report. Thank you.
Okay, good afternoon, Doc Cyril. Good afternoon, classmates. So my report will be on spiral growth of F faces. Let's start. Okay, so what are F faces? F faces or flat faces are crystal surfaces which are parallel to at least two of the most dense rows of atoms in a crystal. And spiral growth generally starts from screw dislocations. Now, to recall, screw dislocations are topological defects on a crystal lattice. So if we trace the atoms around the dislocation, we will shift the lattice plane by one layer, similar to a spiral staircase. So the Burger's vector is parallel to the dislocation line for screw dislocations. Now, an interesting property of spiral growth is that the step itself does not disappear, and growth continues even without the creation of a new step. So spiral growth looks something like this, as shown on the photo on the right. Okay, so before we proceed, some relevant terms for the spiral growth of F faces. We have the rate of growth of the crystal face itself, which is denoted by R. We have the step density denoted by P. We have the distance between successive turns denoted by Y naught, and the rate of advance denoted by V. So now I will share the simplified model for the shape of a growth spiral. For this, we have to lay down some assumptions. First of which is that the spiral is square-shaped for simplicity, and that the rate of advance, p sub infinity, is the same in all directions. So this would look something like this, as illustrated in the figures A through E. This represents the top view for a screw dislocation, and how the spiral growth propagates. So what's happening here is that the growth starts from the surface created by the emergency point of the screw dislocation, creating a new surface normal to the first. So this is illustrated between figures A and B, where the growth from surface in figure A creates another new surface, as shown in figure B. What happens next is that the new surface will not grow while it is shorter than the critical 2D nucleus length, 2 rho sub c. And with this in mind, the distance between two turns of the spiral is 8 rho sub c, as shown here in figure E. This is due to the assumption of a square-shaped spiral, as well as the assumption of a critical 2D nucleus length of exactly 2 rho sub c. Okay, so despite this being a simplified model, there are still some takeaways. So first is that the spacing between the steps originating from a single dislocation is proportional to the critical radius, and the length of the step coming out from the emerging point of the screw dislocation will always be equal to the critical 2D nucleus length 2 rho sub c. Next up is the BCF theory for the shape of the growth spiral. So BCF stands for the names of its major proponents, who are Burton, Cabrera, and Frank. So they were able to provide a more accurate approach for describing the spiral shape and interstep distance. So for instance, shown here in the illustration and at the right, so the velocity vector for the rate of advance is further broken down to two components, which are VR, which is the component along the radius vector, and V rho, which is the component of the velocity normal to the step. So the BCF theory establishes a relationship between step distance and angle from the point of emergence. Here we have the equation R equals 2 rho psi, which is an example of an Archimedean spiral where the radius is a function of angle. So another one of their findings is the interstep distance, shown here as 19 multiplied to Rossi. So what are the implications of these findings? First is that the rate of step advance will vary from 0, right at the center of the spiral, to the rate of advance of straight steps, which is approximated when we assume that the radius of the step is infinity. Okay. So another implication of this theory is that the first turns of the spiral will move more slowly than the more distant ones. This is to preserve the interstep distance between the successive turns of the spiral. Okay, another topic I would like to discuss is spiral growth from multiple dislocations. So we expect a difference in response or difference in the nature of the growth spiral when there are multiple dislocations on the crystal surface. So for instance, we have closed loops forming due to dislocations with opposite signs, meaning opposite directions or of propagation. So when the distance AB, as denoted here in the figure, between the emergency points is greater than the radius of the critical to the nucleus, or 2 rho sub c. Next, next case. Okay, another case is when we have a pair of dislocations of like sign, meaning that the direction of propagation for the dislocations are the same. So if they are separated by a distance much larger than the radius of the critical to the nucleus, the separation distance is L as well for successive turns of this growth spiral. So that is an interesting occurrence. And another case that we would like to see is for a pair of dislocations of like sign separated by a distance much smaller than the radius of the critical to the nucleus. So the separation distance for successive turns of this kind of multiple dislocation setup is half the interstep distance caused by a single dislocation. So those are some of the cases that are commonly studied as well. The last topic I would like to discuss is growth from a vapor phase. So basically, this is the equation for the spiral growth rate from a vapor phase. So we have R, which is the growth rate, is equal to some rate constant multiplied to the supersaturation squared divided by sigma sub c, which is a characteristic supersaturation, multiplied to the hyperbolic tangent of the ratio between the characteristic supersaturation and the supersaturation of the system. So this is the main equation for vapor phase spiral growth. So we can examine further some special cases. For instance, for very small supersaturations where the ratio sigma c divided by sigma is much greater than 1, we can basically cancel out the hyperbolic tangent factor, and we are left with R equals C multiplied to sigma squared over sigma sub C. So this is a parabolic relationship between growth rate and the supersaturation. On the other hand, when we have a very large supersaturations where sigma is much larger than sigma c, we are left with this relationship of R equals C sigma, which is just a simple linear relationship between the two variables. So the relationship between spiral growth rate and supersaturation is shown on the right side of the slide, where there is also an indicator for the threshold of sigma c in supersaturation. So below sigma c, the relationship between supersaturation and the growth rate is parabolic. So this is due to the fact that for low sigma, the diffusion fields of neighboring steps do not overlap, and most adatoms re-evaporate before joining the growth sites. Whereas for supersaturation levels above sigma c, there is a linear relationship with growth rate because the density of kinks on the surface is high, and that every adatom is incorporated into a growth site before re-evaporating. Okay, so that's the end of my report. These are my references. Um, Thank you for listening.
Okay, so this is an introductory subchapter of chapter 4 meant to give us some basic concepts and definitions on epitaxial growth. So marami na nasimulan si ma'am kanina. Hopefully, I can add few things to that. So halos itong content ng presentation ko na cover naman. Okay, so oops. Okay, so here is the outline of my talk. So we will tackle the basic definition of epitaxy, what to take note during epitaxial growth. We will talk about lattice misfit, some jargons encountered in epitaxy, yung historical background, so the rules of Royer, and some current technologies in characterization and growth techniques. Okay, so again, na-discuss na to mostly ni ma'am. So first of all, what is epitaxy? Uy, may ano pa. Complete. Okay, so epitaxy is from the Greek words epi, which means on or upon, and taxis, which means order. So in a more definitive sense, epitaxy describes the oriented growth of one crystalline material on the single crystal surface of a different material. So here are some cartoons of epitaxial growth. We can see one crystalline material called the deposit, so ito yung mga deposit, being deposited on the single crystal surface of a different material called the substrate. So take note, single crystal surface. It can't be amorphous or polycrystalline, for example. Okay, so makikita natin mamaya the difference between crystal growth and epitaxy. Right? So in epitaxy, it is important to note the number 1, crystallographic orientation of the substrate. Number 2, the crystallographic orientation of the deposited crystal. So hopefully we are all familiar with the crystallographic orientations or crystallographic planes, crystallographic directions. So basically here, the substrate and or the deposited crystal can be oriented with the 111 phase, 001 phase, 110 phase, etc. exposed. So here are some of the given planes for this copper material. Okay, so here let's say we want to perform epitaxial growth of copper on a silver substrate. Here we can see two cases. For the first case, we have the 111 plane of copper exposed and the 111 plane of the silver substrate exposed. So if we grow this on top, so 111 plane of copper on top of the 111 plane silver. Now for this second case, we have the 100 plane of copper exposed. Epitaxially grown on the 111 oriented silver substrate. So don't be confused here. You might think, 111 plane, di ba usually diagonal, di ba? Kapag na-encounter natin before, the 111 plane is diagonal. Pero dito, bakit siya flat? So this is because we made it in such a way that the 111 plane is exposed. So siya yung nasa along the XY plane. Okay, so in this case, it is the 100 plane exposed. So siya yung nasa XY plane. Additionally, we have a third thing to keep in mind, and that is the relative orientation of the two crystals, usually called the epitaxial orientation. So here, again, we have the 111 plane of copper, 111 oriented copper, epitaxially grown on 111 silver. But we need to take into account the epitaxial orientation. So here is the 100 direction of copper parallel to the 100 direction of silver. So in our book, it is written like this. So 111 planes, 111 plane of copper, tapos 111 plane of silver, and then you have the directions 100 for copper and 100 for silver parallel to each other. Okay, so what about other cases? So here, everything here has their 111 plane exposed, okay? So for this case, we have the 110 direction of copper, and for the other case, we have the 100 direction of copper. So say we want to grow this orientation. So we take the 111 plane of silver, 111 plane of copper, and then we need to have the directions 110 for copper and 110 for silver parallel to each other. So imagine na lang na this plane of atoms is epitaxially grown on top of this plane of atoms. Now for the second case, we have the 100 direction. We rotated this figure so that the 100 direction of copper is parallel to the 110 direction of silver. So that's what we mean by these three things here. So crystallographic orientation of the substrate, crystallographic orientation of the deposited crystal, and the relative orientation or the epitaxial orientation of the two crystals. Okay, so in general, the epitaxial orientation is determined by the condition of the minimum free energy of the system. So usually dependent on the growth temperature, it might be dependent on how your atoms, how the deposited atoms move or form themselves on top of your substrate. Okay? Wala siyang general rule na kapag 111 plane yung silver mo, automatically you have this orientation. Okay? So it depends on your growth parameters. Now, of course, this was discussed earlier. So we go into the lattice misfit. So the lattice misfit just tells us how different the lattice parameters or the atomic spacings of your deposit and substrate are. So as an example, let's look at silver grown on gallium arsenide with this orientation. Okay, so so here we have the 011 plane of silver with this atomic spacing. So across the rows, we have 4.086 angstroms, and along the rows, we have 2.889 angstroms. So yeah, silver on gas. Next, we have this plane 001 plane of gas, gallium arsenide. Okay, so for this case, we have this atomic spacing, okay, 3.9973 angstroms. Now we will see later why we chose this atomic spacing and not the atomic spacings aside. Okay. So the lattice misfit is given by this equation times 100. Okay, so here B is the atom spacing for the deposited layer. A is the atom spacing of the substrate. Okay, so here are our deposit and the substrate. So for this case, the lattice misfit is positive 2.22% across the rows. So here we, of course, across the rows, yeah. So B is this value here and A is this value here, and negative 27.7% along the rows. So we use B equals this value here and A equals this value here. So here is a schematic of what transpires when you grow silver on gallium arsenide. So here we can see how the compression or the stretching by the lattice misfit occurs for these two materials. So for across the rows, we can see here that the silver atoms is offset or has a misfit according to the this value of the gallium arsenide. So kaya yan yung choice natin for the A. Okay, hindi yung side kasi ganito siya oriented. Okay, so and along the rows, again, this is the diagonal shown earlier, 3.9973 angstroms. So for along the rows, we have a lattice misfit of 27.7% kanina. No? So B is this value here and A is this value here. So hopefully, through this figure, we have seen how lattice misfit occurs when you grow something on top of the other. So hopefully nakita natin kung paano nag-compress or stretch across the rows and along the rows. Additionally, we can notice that along the rows, 4 atom spacings of silver nearly coincide with 3 atom spacings of gallium arsenide. So the lattice mismatch here can be expressed as 4B, since we have 4 atomic spacings of silver, and 3A, since we have 3 atom spacings of gallium arsenide, which gives us not 27.7%, but only 3.6. Essentially, we have only 3.63% lattice misfit. So here we can see that 3 atom spacings of gas nearly coincides with 4 atom spacings of silver. So again, this is not accurate. Makikita natin mamaya kung bakit. So across the rows, we have F equals positive 2.22%. So this is for the silver, for your deposit. So since we have a positive value here, which means that our silver has a greater atomic spacing, and the gas has a lesser atomic spacing. So basically the silver will get compressed to the gas lattice parameter, kaya siya compression. And along the rows we have negative 3.63%. So along the rows you have smaller atomic spacings for silver, which means that when you grow it on top of a greater atomic spacing of gas, the silver will get stretched. Okay. Now we have these 3 words. So homoepitaxy, heteroepitaxy, and autoepitaxy. Before we look into their definitions, let's first ask the question, what makes crystal growth and epitaxial growth different? So again, this was discussed earlier by ma'am. For crystal growth, basically, the substrate and deposit have identical geometry and chemical potential. So again, we recall our previous lessons for crystal growth. If, for example, we have silicon seed crystal or silicon substrate, if we grow silicon on top of it, basically, you can get something that is just that will be an extension of your silicon seed crystal. So for that case, identical yung geometry nila. Since you have silicon bonds, same yung chemical potential, and then it is essentially just crystal growth. Okay. On the other hand, epitaxial growth. For epitaxial growth, we have the substrate and deposit differ energetically and geometrically from each other. So for homoepitaxy, difference of the chemical potentials of the substrate and deposit is mainly due to the lattice misfit rather than difference in chemistry. So yeah, we will look at this on the next slide. And for heteroepitaxy, the difference of the chemical potentials of the substrate and deposit is mainly due to the difference in strength of bonds, irrespective of the value of the lattice misfit. So here are cartoons for homoepitaxy and heteroepitaxy. So homoepitaxy, basically you have the same materials. So this might get confusing kasi you might say that this is simply a case of crystal growth, right? So homoepitaxy, meron siyang boundary layer where misfit can happen. Okay, so basically that's the difference between homoepitaxy and crystal growth. So for crystal growth, homogeneous yan. From your substrate to the deposit, you can't really tell each other apart. So homoepitaxy, although you have the same materials, the same materials for your deposit and substrate, somehow may lattice misfit sila, may boundary sila. Okay? And then for heteroepitaxy, the difference of the chemical potentials is due to the strength in bonds, irrespective of the value of the lattice misfit. So since you have different materials, so diamond on top of another material, you have different bond strengths. Obviously, since you have different bonds. Okay. So historically, Lewis Royer coined the term balik tayo, autoepitaxy pala. So autoepitaxy is basically some researchers simply call crystal growth autoepitaxy. Okay? So yeah, crystal growth is sometimes synonymous to autoepitaxy. So Lewis Royer coined the term epitaxy in 1928 from his extensive study on the growth of ionic crystals on one another and on mica. So ito na-discuss na ulit ni Ma'am previously. So here are key set of rules. For the first one, the crystal planes in contact must have one and the same symmetry and closed lattice parameters with misfit not greater than approximately 15%. Noting that we can compare not only the unit but also the multiple of the lattice parameters. So yung question kanina that arose from whether if you have misfit less than 15%, automatic ba siya na epitaxy? So my take on that is no, hindi siya automatically epitaxy kasi again, epitaxy, to differentiate it from crystal growth, is not about the misfit actually, but about the difference of your substrate and your deposit. Okay? So whether or not your misfit is greater than 15% or less than 15%, as long as yun nga, you take into account the chemical potentials, the structure, the bond strengths, okay, so that's what determine epitaxial growth. Okay, not the misfit. And of course, kanina, we saw that you can calculate the misfit to be 27.7%, but if we take into account the multiple of the lattice parameters, bumaba siya to 3.63. So I think the number, the 15% here is the, I'm not sure, but it could be the upper limit of the misfit without taking into account the multiple lattice parameters. Okay. So for the second rule of Royer, both crystals must have one and the same nature of chemical bonds. Now again, these rules were formulated way back in 1928. So nagsisimula pa lang yung epitaxial growth dito. And actually now, sa current technologies natin, sometimes you can actually grow, you can perform epitaxial growth of different materials with different nature of chemical bonds. So you can grow van der Waals materials on gallium arsenide, for example. So gallium arsenide is covalently bonded. Tapos you can grow van der Waals materials on top of it, albeit very hard. So mahirap mag-stick, or sometimes you can't get thin films, so pwedeng mag-islands, kanya. So ayun. And then for the third rule, when ionic crystals grow one upon the other, the alteration of ions with opposite signs across the interface should be preserved. So I think this arose from, of course, ionic bonding, kailangan preserved yung charges mo. So you can look at it in the perspective of defect equations, for example. So sa defect equations, usually it is done on ceramic materials na mainly ionic. And sa defect equation, the charges should be taken into account. So whatever missing charge you have sa left side ng equation should be taken into account on the right hand side of the equation. So the charges should be preserved. Now we move on to the current state of epitaxial growth, focusing on the characterization and growth techniques. So for characterization of grown deposits, we have these techniques here. So we have reflection high energy electron diffraction, low energy electron diffraction, X-ray, XRD, and some electron microscopy techniques. So XRD, SEM, TEM, OJ electron spectroscopy, AES. So we also have atomic force microscopy, things like that. So for the read, this is actually a very useful tool in MBE in particular, since we can perform in situ characterization of the material while it is growing. So we have this thing called read oscillations. So we have, for this column here, we have a film, and then we grow another film on top of that. So of course, hindi naman siya diretso film agad, malinis. Sometimes you get 3D growth, islands, and then the islands start to coalesce to form your new layer. Okay, so using reflection, high energy electron diffraction. So basically, if you have a clean, very smooth layer, your diffracted electron beam has a very high intensity, very high read signal. So intensity, yeah. And then as you grow, as you deposit material on the pristine thin film, you have some diffusion of the electron beam. So since na-diffuse siya, your read signal decreases. So the intensity of the read signal decreases. And then for this case, wherein the surface is so rough, the intensity is the minimum. Okay, so sobrang diffused yung electron beam mo, diffracted electron beam, you have very low intensity for the read signal until you have the island coalescing with each other, and then nagiging clean na ulit. So tumataas na ulit yung intensity mo. After a while, you have a new layer, very clean na siya, very flat. So you have your read intensity signal to be on the maximum again. So basically, by counting the peaks of the read intensity signal, you can count how many monolayers you have grown. So for this case, we have grown one monolayer. So from here, nag-grow tayo one monolayer. So isa lang yung. Then you have another monolayer, another monolayer. Okay. Now, XRD, SEM, and TEM, we have, these are very common techniques. So XRD, of course, can tell us about the planes and what kind of materials are there in our thin film. So for SEM and TEM, direct imaging of for this example, cross-sectional transmission electron micrograph of gas quantum well, and gas and as superlattices. So yeah, that's what we can get when we use TEM. For OJ electron spectroscopy, this can be used to determine quantitatively the chemical or atomic species present on our films, grown films. And for AFM, we can look into the surface roughness of the film, so whether it is very smooth or very rough. Now for the growth techniques, okay, we have a few here which differ from each other based on the precursors or the sources of the differ from each other based on the sources or precursors that you use for your growth. So we have chemical vapor deposition, CVD, metal organic CVD, molecular beam epitaxy, liquid phase epitaxy, and atomic layer epitaxy. So here is a schematic illustration of some sources or precursors that you can use for epitaxial growth. So for A, we have evaporation of solid sources for MBE. Yan. And then B, utilization of gas sources for metal organic molecular beam epitaxy. So different yung precursors and sources mo. So for MOCVD gas sources, usually the atoms that you want to use is incorporated in a gas or metal organic gas. So usually silanes, phosphanes, ganyan. And then for C, hydrodynamic delivery of gas sources in metal organic vapor phase epitaxy. So dito naman, gas sources, the atoms that you want to grow is carried by the gas sources. Okay, so in summary, we have looked into epitaxy and compared it to crystal growth. So again, sa question ni Ate Che kanina, wherein if 15 yung misfit ba yung nade-determine ng epitaxy, kapag less than 15% ba, automatically epitaxial growth ka na. Okay, so the answer is no. Epitaxy is a subset of crystal growth. So, yan, subset siya ng crystal growth basically. But you can perform crystal growth na hindi epitaxial growth. Okay? Kahit yung misfit mo is less than 15%. So, again, epitaxy, kailangan may preferred orientation ka ng substrate, may orientation ka ng deposit, and may relative orientation sila compared to each other. Okay? We have looked at lattice misfit and yung image natin kanina hopefully helped us realize how the compression or stretching occurs depending on the orientation of your substrate and deposit. So we have talked about some jargons encountered in epitaxy. So yun nga, na-discuss previously, homoepitaxy, heteroepitaxy, autoepitaxy, which is synonymous to crystal growth. And we have looked at current technologies in characterization and growth techniques. So that's all for this talk. Here are my main references. Yeah, thank you.